Agnieszka, so just some background, she got a PhD from the Technical University of Berlin in 2011. From there, she had 3 postdocs at the Technical University of Braunschweig, EPFL Lausanne in Switzerland, and the University of Minnesota. She's joined the KU Math Department in August 2016, so she's been with us a couple years at this point. I should say, she also got an award from the Simons Foundation, which is quite nice, collaboration grant in mathematics. And a lot of this is she's very much a expert in numerical methods and really likes to work in more applied math. And should also say you should listen to this. She likes collaborations a lot, so if you listen to this and you find something that's interesting, go and talk to her afterwards or ask questions after the talk. So based on that, she's going to tell us about eigenvalue problems. So let's welcome Agnieszka.
So first, let me thank Ian and the committee for inviting me here, and I'm really looking forward to this opportunity to talk with so many experts in the field which is so close to mathematics. And as you see, my title is Chasing Eigenvalues in Breakthrough Applications, and I will try to tell you a lot about what applications we already working on. But actually, I think the title is more me chasing the eigenvalue problems in other departments at KU. So I will start with physics, and I hope that some of the topics that I will talk about today will maybe some of you will recognize something that you actually see in your research and you say, oh, hey, I have a problem of that type, and maybe there is something we can do together. So as Ian mentioned, I'm really happy to be here, and I'm really looking forward for some follow-up from this colloquium today. So over my talk, I will first introduce you and walk you through some basic eigenvalue problems which many of you have seen in your education and linear algebra classes. And then I will move to a very particular part of my research which is connected to the so-called nonlinear eigenvalue problems. And this is a part which I have been collaborating with several people, and I will mention those collaborations during my talk. Okay, since it's a colloquium in physics, I looked, and from the point of view what I have been looking at over the years, I tried to see like what are the problems that physicists are kind of providing in terms of eigenvalue problems. And the main object of the talk today, later on, will be the so-called nonlinear eigenvalue problem. So we will see that the classical linear eigenvalue problems, which you know and you're familiar with, are just a special case of that nonlinear eigenvalue problem. But what we are interested in are problems which can be stated in the following form. You can think about t being a matrix valued function, so which is dependent of lambda. So if I fix lambda and evaluate t of lambda, this will be a matrix. But now we are looking for all lambdas, which are complex numbers, and associated x's, so vectors, such that t lambda of x is equal 0. So if I find a lambda and x which satisfy this equation, I'm calling lambda an eigenvalue and x an eigenvector of the nonlinear eigenvalue problem. The classical linear eigenvalue problem is a very specific case. If you think of t lambda as a minus lambda times identity, then you will get your classical linear eigenvalue problem. I will mention that further. Some of you may be aware of nonlinear eigenvalue problems which are stated in a slightly different way. They are classical nonlinear problems when the nonlinearity is in the eigenvector. So lots of those problems when the nonlinear dependence is on eigenvector, not an eigenvalue. So these are also very common types of what are called nonlinear eigenvalue problems, that they're of different nature. So some examples which I will talk more about the photonic crystal example, but if you think about photonic crystals, how we model photonic crystals, so we are thinking about them like in terms of like semiconductors of light. And what scientists are interested in is if we can find a way of transforming a wave into a certain frequency through a medium which we call a photonic crystal. So it's a propagation of light, and what we are actually trying to do when you try to find materials with those specific properties, you study Maxwell equations and their very particular formulations, but at the end of the day, when you discretize your problem, and what you are actually doing is solving some nonlinear eigenvalue problem, and we will talk about that. So recently there is lots of also interest in nanoelectronics. There are lots of nonlinear eigenvalue problem in that form, in design of new in chip design. And very recently I got aware from some colleagues on Berkeley laboratories that they have some collaborations with particle physicists in Fermilab when they are studying this particle accelerator cavity, and it turns out that the problems of interest there are also nonlinear eigenvalue problems. Okay, so to motivate why we are actually interested in eigenvalue problems in very different settings is, some of you probably have heard, sorry for that. I disconnected myself not to get pop-ups, and then that wasn't. Okay. Come on. I'm sorry for that. So some of you may have seen this famous, there are multiple movies, YouTube movies about this phenomena that was Tacoma Bridge in beginning of 1900. And we have this beautiful phenomena of bridge balancing. They called it even galloping Gertie. So this is a bridge. This is not the rubber or any experiment. This is a bridge, a very solid construction, as you may think. And this is basically the bridge wobbling and moving in all possible direction. And I think in a moment you will see the end effect. So yeah, there is a car, and there was a dog that someone was trying to save before the bridge collapsed. Okay, so we have this phenomena of steel and metal construction wobbling for a while, and then at the end it turned out that the bridge collapsed. Okay. So whenever I talk about the eigenvalue problems, I always show it to my students, and they're like, it's not possible, it's not happening, this was years ago. Well, if you Google bridge collapses, you will see that in 2011 there was a similar problem with the Millennium Bridge in London, so it seems that this is not only a problem of from the beginning of 1900, but it's also a problem which have been coming back in different setups. Okay, so how this wobbling bridge is connected to A, physics, and B, to eigenvalue problems. So I don't have to convince you that it's connected to physics. So you all know about the frequencies and natural frequencies. So those of you, that's a classical Wikipedia definition. So every system has something which is called a natural frequency, which basically is the frequency if you put the system into the motion. So if I think about this very simple spring which is clamped on one end, and I put the mass, and I basically take the displacement of this mass, so I just lift it up or down, and I release the mass, it will start to oscillate, and then it will oscillate with what is called the natural frequency. So then we also have another phenomenon. So phenomenon of resonances is basically there are frequencies that the system can oscillate on a very, very high amplitude. So basically, you will put the system into motion by applying an external force, and it will start to oscillate, but we will see that these oscillations will eventually not damp out, but they will be, the amplitude will be getting higher and higher. We lack this phenomena in certain setups. So those of you who play a musical instrument, this is how we get the sound because of the occurrence of those resonances. But we also have obviously the undesirable resonances. And one of the examples which you always and I'm not going to show it because apparently it doesn't work. I'm sorry, but you can do an experiment at home. You can put a empty glass of wine in front of the speaker and put the volume as high as you can. Then basically you will see that eventually if the volume is too high, your glass will break. So these are undesirable resonances, and we definitely don't want that. Okay, so the resonances occur when the frequency of the external force that we apply become very close to natural frequency of the system. So that's basically, as you will see, an explanation for this wobbling bridge and the bridge which eventually collapsed. But that was the question, where is the eigenvalue problem? We understand, you all understand the physics, but how I can see the eigenvalue problem that is behind this whole system. So we can think about very simple example if you're all familiar with the Hooke's law. So we have basically the classical vibrating system. We have the force, so we have the second derivative of the displacement. So we have the force, and it's proportional to the spring constant and the displacement. And if we assume that the solution of x, so the displacement, is of a certain form, involving a component u and e to lambda t, and we rewrite what this equation actually is. So the classical exercise from differential equation, turning it into a system of linear first order differential equations, we basically end up that in order to describe the solution of the system, we have to solve this eigenvalue problem. So we search for lambda, which is the frequency, and we have an eigenvector v. So this is basically the very simple k and m are just the mass and the spring constant, and we have a very simple matrix, 2 by 2 matrix, generalized actually because we have an additional non-identity matrix here, eigenvalue problem. Okay, so we can think about what happens in the multiple dimensions. So we have now the matrix, the mass matrix, and the stiffness matrix. So we have now the vector x, so the higher dimensional, that n equals to 1. And if we do the same substitution, so we assume that the solution has a certain form, this will allow us to write our eigenvalue problem, but now we have an eigenvalue problem of matrices which are not just put 2 by 2, but dependent on the size of matrix K and M. So this is one of the classical generalized eigenvalue problem which every one of you is familiar with, and you see it very often in any basics physics or math classes. Okay, so what does it have all to do with the Tacoma Bridge? So as I told you, that the resonances occur when there is an external force which has the frequency very close to the natural frequency of the system. So what happened with the Tacoma Bridge, this was a construction which had 840 meters length and the width of 12 meters. There was, of course, the eigenvalue problem of this bigger type that I showed you, connected, which you can write connected to the nature of the structure. And what it turned out, that this day it was very windy, so there was a wind of 68 kilometers per hour, and the frequency of the external force, so the wind, was very close to the natural frequency of the bridge. What it lead to is basically this external frequency was so close that it matched the natural frequency, and this amplitude started to be higher and higher and higher, and so the bridge started to wobble in any possible direction, the angles, and away from its original position, and eventually the resonances were so high that it collapsed. Okay, so that was the one application which is kind of very natural for physics, but I like the other one, how the eigenvalue problems come in other disciplines. So all of us use Google, and most of us know that there is Google has behind an engine, the search engine, which is basically the PageRank algorithm. So it's an algorithm which decides which of the web pages are listed first as the one which are most important or less important for us. So how is the PageRank algorithm connected to eigenvalue problems? So you can think about PageRank algorithm as a contest for who is the most popular person in your group. It's basically which of the web pages is the most popular one. This one will appear on the top of your Google search, and the others will appear below. So PageRank is a probability distribution to represent the likelihood that if you start clicking from one page at the beginning, what is the probability that after a certain amount of clicks you will end up with some particular page. So if you consider now the network when you have n websites, and we have a certain importance measure. So we measure the importance of some particular web page as j by the sum of the importance of all other pages which are linking to it. So basically, if I'm sitting on one web page, how popular is my web page? Well, first I'm looking who is connected to me, and on the other on the other hand is if someone is connected to me, how popular this person is. So how popular is the web page that is linked to me? Okay, and so we can measure popularity or the importance of every single web page in the network using this formula. So to give you an example, consider a network of 3 web pages. Okay, so how important is web page number 1? Well, there is only one other page linking towards it, so it's popularity of this web page 3, and the weight, okay, this is only one link, so this is the weight which you put. Okay, what about 2? Well, 2 is in the situation that there should be a 1 here. That 2 is there is only one web page linking to it, so it's popularity of S1 times 1, there should be 1 here, because that's what is the weight of number of links that are going towards 2. And then we also have 3. And 3 we have, it's a measure of how many, what is the popularity of the web page 1 linking towards 3, what is the popularity of 2 linking towards it, plus the weights. Okay, so if you put all of that together, it turns out that this is the matrix that you got from those weights. This is a vector which contains the popularity or the importance of each web page, and you have it also on the right. So if you look on this is nothing else as an eigenvalue problem, ax equal to lambda x, where lambda is equal to 1. So what you're interested in this setup is you want to determine the importance of each of the web pages. So in order to determine how important is the web page 1 or web page 2 or web page 3, you have to find an eigenvector associated with the eigenvalue 1. Okay, so how you can do it? Well, one of the methods that is very popular in terms of determining the dominant, we can also prove that it's a dominant eigenvector, is the power method. So we take the probability, we are starting to walk in our network. So we take the probability, pi of 0 is the probability that a user is at the website Si. So I'm sitting on one website at the time 0. And now I start to click. I start to move with the time to another website. Okay, if the user moves that the probability that he's on the website Sj at time 1 is given basically on this, in this formulation. So basically, I'm looking on this matrix of the weights, what possibilities I have to move from a web page 1, and then I'm summing the entries in that weight matrix times the probability that which tells me what was the probability to be on the previous page, and I'm doing it iteratively. So if you start clicking after k steps, you see that in the step k plus 1, what you basically are doing, you're applying a to the previous probability pk, and this one you applied a times a to the pk minus 1, and so on. So you have the powers of matrix A, and that's what we know as a power method to solve the eigenvalue problem. Okay, so there are a few things that we would like to know. Does the equation that I showed you always have a solution? Will the solution have an entries that are non-negative? These are probabilities, so we want to make sure that the probability is non-negative. Is the solution unique? If not, what we know about the case when it's not unique, because if you can imagine, we will have conflicting rankings. We try to rank something and we will have two solutions. So from the theoretical point of view, there is a beautiful theorem, and I think that it's the whole power actually of the PageRank algorithm is in this theorem, which is the so-called Perron-Frobenius theorem, which says that for any matrix that have all entries non-negative, and our matrix has an entries which are non-negative because these are connected to the weights, and each column summing to 1, these are the probabilities, the eigenvalue problem ax time equal to 1x has a non-negative solution. So we know that the solution exists, it's non-negative. Actually, there is a very specific statement about how we can ensure a uniqueness and what happens, in what cases we may expect to have a conflicting rankings. So as you see, the linear eigenvalue problems are living around us in very different setups. So in construction, like civil engineering constructions like bridges, in Google search, they are everywhere. What about nonlinear eigenvalue problems? These are very different objects and they have very different nature. So we would like to know where are they appearing? Are they as natural as linear eigenvalue problems? And if they are appearing, how we can actually handle those. So I gave you a brief definition of the nonlinear eigenvalue problem, which I'm completing now. So we're interested in some scalars in the complex set, and we have a matrix valued function t, which maps from the subset of complex numbers to the matrices. So this is basically this matrix valued function. And the nonlinear eigenvalue problem with the nonlinearity in the eigenvalue consists of finding all the scalars, which we call eigenvalues, and non-zero vectors such that those equations are fulfilled. Okay, so in principle, the difficulty in this formulation of why is it so different from the linear eigenvalue problem is that t can be any arbitrary function of lambda. And I will show you several different cases. So we can think about polynomials, we can think about rational functions, we can think about exponential functions as well. So just to walk you through and let you know about some very particular intuitions that you may have, and then in the case of nonlinear eigenvalue problems, they're actually not so straightforward. There is a nice table comparing different cases of nonlinear eigenvalue problem. So if you set t of lambda to be a minus lambda times identity, you will end up with a standard eigenvalue problem. So the easiest case, which you know, and you know that if you have a size of the matrix A is a square matrix of size n, you have n eigenvalues associated with this eigenvalue problem. We also have a generalized eigenvalue problem, so you know that you have now a pair of a pencil, a pair of matrices A and B of dimension n. Then if t of lambda is equal a minus lambda b, then you have the generalized eigenvalue problem and still the matrices of dimension n, so you have n eigenvalues. But the moment you start to move to the more proper, what we call nonlinear eigenvalue problems, the situation changes dramatically. So one big change is if you consider t of lambda equal to lambda squared A2 plus lambda A1 plus A0, where each of this matrix, A0, A1, A2, they are coefficient matrices which are of size n by n. And if you try to solve the associated problem, so you multiply it by x and look where this problem is equal to 0, it turns out that although the matrices, the coefficient matrices are of dimension n, this problem has 2n eigenvalues. So you have more eigenvalues than the dimension of your coefficients. If you can write it in general form, you can put as many of those coefficients, matrix coefficient, as you like. So you have the polynomial eigenvalue problem. And then the number of eigenvalues will be n times d, which d is the number of the coefficients which you have in your polynomial eigenvalue problem. Okay, but then we are in the most general case, in a sense, when we have what we call the proper nonlinear eigenvalue problem, when you basically have coefficient matrices, but now you have, in front of each coefficient matrix, you have an arbitrary function of lambda. It can be exponential, it can be any function you want, it can be rational function. And then actually we know that if we have a problem of that type, we may have infinitely many eigenvalues, despite the fact that the coefficients are standard matrices of the finite dimension.
But could I just quick question?
Yeah.
So this number of eigenvalues for the nonlinear problem, this is only give you the maximum possibility, but in real case, in many situations, actually it's much smaller than.
Yes, this is the maximum
so
number.
This is misleading.
Well, this is including multiplicities, right?
Yeah. So not in especially in the nonlinear case. So in a lot of situations, you only have a finite number of the eigenvalues, even though the maximum value is infinite. But a lot of those values are non-analytic or not in the real space. Or in a lot of cases, not existing.
Well, we are considering complex sets, so we allow complex eigenvalues also. They don't have to be on the real.
Yeah, even in that case, it's in a lot of systems, it's just finite number.
I will give you actually one example in a moment when you will see actually that you have infinitely.
You could have system as an infinite number of eigenvalue, but it's not always true.
Well, this is the upper bound, right? So we may have multiplicities and things like this. Yes. So you know certain things about classical eigenvalue problems, which are nice and help us a lot when we are handling those problems. But then we have also, we are trying to extend our intuitions from the linear problems to the nonlinear problems. And actually, this is one of the misleading tracks and things that makes the things very complicated. So we know that if we are considering linear eigenvalue problem, then we know that we can formulate the characteristic equation. This is not the way how we do it, but from the mathematical point of view, how you find an eigenvalue, you form a characteristic equation and you find the roots of a characteristic equation. Well, in a sense, if you look on the nonlinear eigenvalue, we have a similar property. We know that the eigenvalues are the zeros of the equation which arise from taking the determinant of this matrix value function T of z. But on the other case, this is the case when infinitely many eigenvalues appear. Even if you have a regular, what we call the regular T, so that the determinant of T of z is not identically equal to 0, we know that even in that case, the eigenvalue problem may have infinitely many eigenvalues, which we know in the case of intuitions from linear eigenvalue problems that are very different. The other thing which is very disturbing, and it's, I think, one of the most difficult parts in terms of treating those problems numerically, is that the eigenvectors associated with the distinct eigenvalues don't have to be linearly independent. So I have two distinct eigenvalues, and I know from the linear eigenvalue problem that if I have two eigenvalues which are distinct, each of them has an eigenvector, and these eigenvectors are linearly independent. Well, in the case of nonlinear eigenvalue problem, it's not anymore true. You can have the eigenvalues which are distinct, and they will all share one eigenvector. And I will show you a very trivial example of that. The other thing is also the algebraic multiplicity, which we have been talking about, of an isolated eigenvalue, although it's finite. So the multiplicity is finite, but it's not bounded by the problem size. It connects to the fact that we may have infinitely many eigenvalues, so we have to have some of the algebraic multiplicities which may be larger. And if some of you are interested, there is a vast number of literature. So the first class of survey articles were on the quadratic eigenvalue problems, so really the ones which were investigated at first, then the polynomial, which are very specific, and then the two last are on general type nonlinear eigenvalue problem. So I want to illustrate this point of how the distinct eigenvalues may share linearly independent, may share an eigenvector. So if you look on this very, very simple matrix value function, so T of z is equal, you take this matrix E to I z squared, you have the eigenvalues, you know that the eigenvalues are the roots of the determinant of dz, so these are all the eigenvalues of this problem, okay? So actually what you see here, this is a plot of 42 eigenvalues of this problem. We know this problem has actually infinitely many eigenvalues. So we know that the lambda 0 has an algebraic multiplicity 2, and all other eigenvalues are simple eigenvalues with algebraic multiplicity 1. Well, it turns out that vector 1 and minus 1 is the right and left eigenvector for all those eigenvalues. So the right and left eigenvector are the same, and each of those eigenvalues here, the associated eigenvector is 1 minus 1. So there's infinitely many eigenvalues, and they all share one eigenvector. Well, this is something which is very different than the case that we know from linear eigenvalue problems, because we like it. We know that eigenvectors are linearly independent, so we know they form nice bases. And then very often we are actually looking in eigenbases because they are the right bases to look on some physical problems. Well, we now have a problem because we only have one eigenvector associated with all those eigenvalues. Okay, so if we go back to our vibrating structure, I made a simplification. I assumed that in the previous equation that there is no damping in it. I said that there is mass matrix, there is stiffness matrix, but there was no damping parameter, which of course, if you construct any structure like bridge, there is always a damping involved. So if you involve the damping and you do the same trick as we did before, you will see that you end up with a problem which has that form. And this is nothing else as a quadratic eigenvalue problem. So as far as our problems are polynomial, we know we can always transform this polynomial eigenvalue problem into a linear eigenvalue problem by extending the dimension. So this problem will have dimension n. We just put our matrices, we stack them up, and we have the linear problem of dimension 2n, and that actually explains why we have 2n eigenvalues when we use quadratic eigenvalue problem. So now we see that actually in order to properly model the bridge problem, we should actually look on this formulation when it's a quadratic eigenvalue problem involving damping, mass, and stiffness, instead of simplifying the model as we did before. But the other class of problems which are very challenging, and I was trying to give you some illustration on that, are those photonic crystals. So when we have the photonic crystals and we are modeling them, so this is a 2D photonic crystal, so we have those kind of tubes in stacked together, or cylinders stacked together, and we look basically on the cut through it, so we look on the unit cell. So we know that from a mathematical point of view, the proper mathematical description is the set of Maxwell equations, and what we are searching are those, what they are called the photonic band gaps. So there are these openings in the frequencies that we can use to propagate within them the light of certain frequency. So basically you can think, as I said, they're calling them very often semiconductors of light. So you want to propagate the light as we do in the classical semiconductors. But in order to be able to do it, we have to find those gaps that we can use. Okay, so it's a very simple model. So if we look onto the photonic crystals, and in the two-dimensional case, we can consider the mathematical model, which just takes into account one component of the wave equation, we assume that it's independent in the third direction. We have this electromagnetic wave which can be decomposed into two pieces. So we have the transverse electric, when basically we know that the third component is 0 and H1 and H2 is 0, or we have a transmagnetic description when we are basically setting the electromagnetic wave in direction 1 and 2 to 0, and we are only consider the electromagnetic field in the third direction. So if we use this formulation, we can basically simplify the set of Maxwell equation in the time harmonic case into this equation. So we have the Laplace of the E3, so the third component, depending of course on the position. We have the frequency, the speed of light in the vacuum, and we have this epsilon, which is basically material permittivity. So it's a property of the material which may depend on the frequency, and it definitely depends on the position. Okay, so what we are interested now is to determine the pairs, the frequencies, and the associated u's, which actually are nothing else. When we assume that it's a periodic model, so we have to use some Foucault transform and to be able to state this equation. So basically, U is nothing else as the Foucault transformation of the third component of electric field. And this is the description that we get in terms of a wave vector in the Brillouin zone of our problem. And we assume that the magnetic permeability is equal to 1. Okay, so if I look on this problem now, what happens if my permittivity, so if this epsilon is independent of the frequency, I can take my problem, I can do the discretization, my favorite discretization, and I will end up in this particular problem, which you see is a linear eigenvalue problem. You have a matrix, the stiffness matrix A, and the mass matrix M. You can always write it in their form, but this is a linear eigenvalue problem which you have to solve. Easy. But what happens if your material property, so your material permittivity, depends on the frequency? So it depends where in the material you are, what frequency you apply, the material property will depend on the frequency. Well, then your epsilon is not anymore only dependent on the position, but it's also depending on the frequency. Moreover, it may also depend on where in the material. So if you are considering a unit cell, which part of the material has what kind of properties. So the permittivity in different regions of your material may also be different. Okay, so if you discretize this problem now, you will see that you are not anymore in the linear case, but actually what you are doing, you're having a nonlinear eigenvalue problem, which you are interested again to solve for those frequencies that allow you to determine the band gaps which you can use to propagate the light. So just moving from the independent material property into a frequency-dependent material property, you move immediately from the linear to the nonlinear eigenvalue problem.
For each given mode, so when we solve this in physics, we solve mode by mode. So this is, suppose this U is a Fourier transformation of our original field. Mm-hmm. And so for each given frequency, this is no matter epsilon, that the permittivity depends on the frequency or not depend on the frequency. Your matrix is independent of U, which means it's a linear problem.
It's linear in U, but it's nonlinear in frequency. That's what I said, that they're...
So when you solve the matrix, you solve mode by mode. For each mode, that matrix is a linear matrix. It's a perfect.
If you fix the frequency, that's what you mean. If you fix the frequency, the T of lambda is the matrix.
Yes, eventually my eigenvalue or eigenvector will be frequency dependent, but that is after I solving the matrix. After I solving matrix, the next step I will do the inverse Fourier transformation, which is independent problem, which is not related.
I think we're talking about two different types of nonlinearities, because you're taking you're taking into account that your matrix doesn't depend on you, so in a sense it doesn't depend on the eigenvector.
Yes.
Yes,
so
this is true also here. It doesn't depend on the eigenvector.
Yeah, so what's the problem with this? So this is just a perfect matrix problem, linear algebra problem.
Yeah, this is algebraic nonlinear eigenvalue problem, but it's still nonlinear from the algebra point of view.
Okay, go ahead.
Okay, so now I would just like to talk about some of the new developments in how actually we solve in practice those nonlinear eigenvalue problems. And there is a vast number of methods, but I will just concentrate on those which are based on the so-called Cauchy integral approach. So we are actually interested in solving eigenvalue problems where we are interested in determining eigenvalues which are living inside the spectrum. They are not extreme. They are not the smallest, the largest, but they're living somewhere inside the spectrum. So if you think about it, okay, you give me an eigenvalue problem and you give me a box in the complex plane and say, I want all the eigenvalues in that box. And this is a joint work with some colleagues in the University of Minnesota and some engineers from University of Massachusetts in Amherst. Okay, so how the Cauchy integral methods work in general. So we are interested in, suppose we are interested in computing eigenvalues in the linear case. So if someone will give me a spectral projector, and I apply the spectral projector to a set of random vectors, I will immediately recover the eigenvalues. They will be given for free. The problem is, well, how is the spectral projector defined? The spectral projector on the space on the invariant subspace is basically involving the matrix of eigenvectors. So if I want to solve an eigenvalue problem, I don't know eigenvectors in advance, so I cannot do this trick because that's what I'm searching for. So there was a question how actually you can use the knowledge of the fact that spectral projector allows you to extract the eigenvalues without knowing it. And this this problem comes back to actual complex analysis when we know that the spectral projector associated with the eigenvalues of some matrix A that live in some region on the complex plane is given by taking this expression. So what we are doing, we are taking the resolvent, the inverse of the resolvent of the matrix. We take a contour integral using the contour that we picked. We scale it, and what we get from that is the spectral projector associated with all the eigenvalues which are in this region that we are looking at. So if I can do this efficiently, if I can calculate this contour integral numerically efficiently, I will get the spectral projector, and I can use the spectral projector to extract the eigenvalues. Well, of course, we cannot do integration exactly. So the question is how we can actually use the Cauchy integral approach to extract the eigenvalues.
There's a question here.
Yes.
Does the contour contain some of the eigenvalues?
You mean if the eigenvalues are on the contour, on the boundary?
No, I'm not worried about that. I was understanding the formula. So if I have for this to find one eigenvalue and one-dimensional projection onto one eigenstate, do I run the circle around one of the eigenvalues in the complex plane?
Yes.
And if I find 5 eigenvalues, do I run around those 5?
Yes. So the
get a 5-dimensional projector?
Yes, the spectral projector will be associated with all the eigenvalues which are inside the circle.
Inside the contour
Yes.
of the Cauchy.
Yes, exactly. So this allows us to use the classical quadrature rules to approximate the contour integral and build a scheme, basically, when you do the quadrature rule to approximate the spectral projector, and then use the spectral projector using the classical, what we call Rayleigh-Ritz procedure, so projecting something from a very big space using the spectral projector to a very, very small space. And this allows us to extract the eigenvectors associated with the eigenvalues inside the contour, and then we can easily determine the associated eigenvalues. Okay,
and do you have a Rayleigh-Ritz concept of these nonlinear things?
This is the moment I'm talking about just linear case, the linear case.
That's right.
But we have the Rayleigh ridges also for the nonlinear. But I think I'm running out of time, so I will move actually to some examples that we can do for the nonlinear case. So in the classical, if you want to do the same thing for the nonlinear eigenvalue problems, we write it in terms of the Newton methods. So we first determine the Newton method formulation. And then using the Newton method step, so we have the classical Newton for the eigenvalue problem, we can build, and I will show you, the associated contour integral in the same way using the properties, how we connect the resolvent and the properties of the nonlinear eigenvalue problem. And if you do that, we actually extract this very, very particular space. So the approximation of the spectral projector allows us to pick up the proper space Q and then project on that space and get the corresponding Rayleigh-Ritz procedure to extract the eigenvalues. So let me just show you some of the examples. So we were interested in scattering resonances in one dimension. We know that if we are using just in the real line formulation with absorbing boundary conditions, we can write it in this particular form. When we discretize, we get the corresponding quadratic eigenvalue problem, which is of that form. And this is the whole spectrum of the whole problem. So we picked the dimension such that we can see all 302 scattering resonances associated with this one-dimensional problem. But now the goal is what happens if initially you're interested maybe in some eigenvalues inside a particular region, and you don't want to solve the whole problem and then find out where those eigenvalues are. So what we did, we used this contour integral approach. So we put a contour. This is actually a circle, but it's just skewed differently that it looks like ellipse. We were interested in finding all eigenvalues inside this contour, and the red triangles are all the eigenvalues which we found. We see also that our spectral projector was a little bit was of higher dimension, so it actually captured also some eigenvalues outside, so we may have to filter what is in the region or what is outside the region. We did some discretizations also for the fluid dynamics, so discretization of the Orr-Sommerfeld equation, which gives us the polynomial eigenvalue problem. You see you have the polynomial of degree 4. Again, the spectrum has very nice regular shell that's called a butterfly problem, and we are interested in some particular eigenvalues in the complex plane. And we were able to capture them very nicely depending on how many quadrature nodes we are using. This problem is actually a very old model problem. I looked in the original Handler paper, which is actually in German, but I couldn't find out what is actually where this problem comes from. It's coming from application, that's what people are claiming, but I couldn't trace it back. But what you see here, we have this general nonlinearity that I was talking about. We now have a exponential of lambda, so we are searching for lambda where it's involved in the exponential function. So it's truly a nonlinear problem. And the spectrum, the full spectrum looks like this, with the dimension of the discretization is 200. And we said we are very interested in some eigenvalues very, very close here, so clustered inside. And this is how we can actually obtain the eigenvalues in arbitrary region in a complex plane. And so these are some statistics depending on how many quadrature nodes we have, what is the subspace dimension that we are projecting, because that's also, we need an estimate how many eigenvalues inside the contour we have. And the last example is actually something which we just started to look at is in many engineering applications, instead of solving very nice and big linear problem, people are using boundary element discretizations to lower the dimension of the problem, but then the problem becomes more complicated. So from linear, large, you go to the smaller dimension, but to the nonlinear problem. So if you solve, for example, the Helmholtz equation in 3D, this is for the problem of practical relevance. It's a pump casing, a shape where the pump will be put inside, so it's a metal piece. So we were interested in calculating the eigenmodes inside the spectrum for this particular geometry, and using those same Cauchy integral methods, we were able to determine the eigenmodes. So here are the first 4 eigenmodes. This is very computationally complicated problems because of the whole boundary element discretization in large dimensions, but we can also use those Cauchy integral methods for arbitrary problems of practical relevance. And I think with this, I will thank you very much for your attention. I will be happy to answer questions.
Questions? Yeah, Jack.
So go back to my previous question. So basically, what are all the example problem you present here? It's nonlinear in the sense of the parameter. It's not really nonlinear operator. You are not talking about the eigenvalue of the nonlinear operator.
Well, I'm talking about when you discretize the problem, right? When you discretize.
Yeah, there's a 2 space we can dig. So typically, for example, for the finite element problem, we discretize in a real space x, y, z first off, right? And then of course you will have a parameter space in a frequency domain. For example, you will also discretize the frequency for example, in a photonic problem. The frequency will be discretized because the boundary condition.
Well, you can sample the frequency. That's what you mean, right?
Yeah. So basically, let's back up. So from numerical point of view, you have to discretize something in order to calculate. So if you treat the frequency here as a parameter, for example, all right. So it's nonlinear in the frequency sense. I agree. But when you discretize the frequency.
Oh, sure.
The omega, basically for each frequency, you basically have perfect
linear problem.
Yeah, you have a perfect linear problem. So numerically, basically, you have all the algorithms you can use.
Yeah, basically. Yeah. So if you look, I can look even here, right? If you look on this description, T of lambda, if I fix lambda, or let's look here, if I fix omega, this is a linear eigenvalue problem. Yes, I agree, but that means basically what will happen is if you give me a frequency, I will put it in here, so I will evaluate t in this frequency. Yeah. This will give me a linear eigenvalue problem.
Yeah. So typically, in physics, what we do is we discretize the frequency domain. All right. So on top of discretizing x, y, z, we also discretize frequency. So if we discretize frequency, basically, for example, we slice the frequency into 1,000 slices. So basically, I solve this eigenvalue problem for 1,000 times.
Yes, the linear one.
And then my question is, what's the problem here?
Well, you have to. First is that you have to solve a linear eigenvalue problem, which may be large, for each single frequency that you're interested in.
Million by million matrix.
And actually, you also have to make sure what is happening. If you fix the sigma, you set up the frequency, then you have to solve the eigenvalue problem and make sure that the smallest eigenvalue of this problem is 0. Because then, if the smallest eigenvalue of this linear problem is 0, then it means that this frequency was an eigenvalue of the original problem. If it's not, you don't know what this frequency is. It's some parameter. It may not be an eigenvalue of this problem.
You mean at some parameter I could have singularity in the problem?
If you fix, is there a chalk here? Oh, yeah.
Maybe we can see if there's another question.
Oh, yeah.
Okay.
Well, we can talk, but you're right. You can just discretize the frequency domain and solve associate linear problems.
So, are there any other questions for Agnieszka?
Are there some beautiful things behind this? I mean, one beautiful thing would be that you'd have some relationship between a nonlinear problem of a certain particular type, like a polynomial, and then a higher dimensional linear problem. You could map one to the other.
Yes.
Another beautiful thing would be some notion of invariance. So you have these nonlinear eigenvalues. What's their role geometrically as invariance of some quadratic, some quadratic form, which you almost hinted at when you mentioned with the Rayleigh-Ritz variations.
Well, that's actually a big problem in terms of nonlinear eigenvalue problems. So one thing is, as we know that for a linear case, we have something like a Schur decomposition or some kind of factorization from which we actually extract the eigenvalues. There is nothing like this in terms of nonlinear eigenvalue problem. We can...
How do you know in advance?
Well, maybe there exists, but we are not aware of that.
We don't know of it.
We are not... The other things is in the linear case, we have a beautiful property which is called the min-max principle. So Courant-Fisher, which we know how to order the eigenvalues, and we know that there is a minimization, min-max characterization how to get the eigenvalues out of the spaces. Well, in a sense of nonlinear eigenvalue problems, we only know that certain operators admit what we call the Rayleigh functional, that we can actually extract the eigenvalue from the minimization properties. So there's actually a lot of things which we don't know from the theoretical point of view still to make it even connected to what we know already in the linear case. So there's lots of like underlying operator theory research which has to be done in order to start to understand the geometry or the connection.
Part of that's because there's an infinite number of ways to be nonlinear. When you
Yes.
broke it down and keep it simple with polynomials or something.
For this we have
finite
theory.
order, then you
Yes.
have theorem.
For polynomial cases, we have theory, underlying theory. We have also like forms like Schur complement and things like that, because then you move it all to the linear problem, which you can state and analyze from that point of view. Yeah, but for the truly nonlinear, we don't have any knowledge about that.
So I think we're coming up at 5 and people have to catch buses and stuff. So if you have any more questions, you can catch Agnieszka afterwards. I'm sure she's happy to contact her.
Thank you.